So it's a pleasure to have Sebastian Goette, who will be talking about G2 manifolds and their moduli space.
Yes. Yeah, good morning. And thanks to the organizers for inviting me to this beautiful place. I really enjoyed it. So you are probably wondering why we are having a talk on G2 manifolds on such a nice topological and higher structural representation theoretical conference. I'll tell you in a minute. And if you want to download the slides, the address is here, and it's also going to be on the next two slides. So if you want to download them, please go ahead. Yeah. So the idea of this talk is to give you an invitation to look into problems related to G2 geometry. I'll tell you within the talk in a few places that it's actually a rather analytic subject, but somehow the analysis it seems to be reached a point where it's difficult to go on. So there will still be progress, but I believe that some fresh ideas would be very helpful. So the plan is, in the first talk, I'll give you an introduction to G2 geometry, basically tell you what holonomy is, tell you what holonomy G2 is supposed to mean, give you some constructions, also some obstructions against G2 holonomy, and I'll tell you what the moduli space is. Then we'll discuss some basic invariants from topology. And as one example where topology has helped to understand G2 manifolds better, I want to present the new invariant and give some of its properties and maybe an example or two, but not too complete. And then, preparing for part two, I want to tell you what calibrated submanifolds are. There are two of them, or two kinds of them in G2 manifolds. And I'll briefly mention instantons as well, just to complete the picture. Then, part two, we'll focus on these associative submanifolds. For some reason, people believe that one should be able to count them just as one would count holomorphic curves in the Calabrian manifold, and then maybe set up some vision homology or whatever. People hope that's true, that's possible in G2 manifolds, and we'll see some problems and some possible ways of tackling them. And I want to introduce you to a topological approach where we don't know yet whether it will be fruitful or not, but at least the basics are kind of understood by now. So we'll modify the Contriagan-Tom construction from modalism theory to talk about associatives by getting basically all the different. And I'll tell you what an H principle is, then I'll tell you that it unfortunately fails in this setup, but nevertheless, I believe it will still provide us with some intuition. And finally, we have to talk about singularities of associative submanifolds, because they tell us something about them in spaces. Okay, but now let's start with the basics. If you are in a sphere, say at the North Pole with a stick pointing south, and you parallel translate your stick while walking down to the equator, then you walk along the equator for a while and return to the North Pole. You haven't moved the direction of your stick, basically, but still, when you are back at the North Pole, you find that that there is a certain angle between the position where you started and where you are now. And Gauss-Bonnet, in fact, tells you that that's related to the area of the triangle you've been walking around. And this is actually the first time where you see holonomy probably in your life. And the holonomy of S2, well, that's the group that you get by current translation along arbitrary loops. At some point, that's, of course, just the rotation group SO2. And from the title, you know that we are going to look at a very particular holonomy group now in 7-dimensional Riemannian geometry. So, parallel translation means we have to solve some ordinary differential equation. We have a vector field along a curve, and this vector field has to be parallel. To talk about this, we need to be able to differentiate. And to make life simpler, I assume that I have a smooth, by which I mean C infinity, structure on a manifold M. So at least theoretically differentiation makes sense. And then I need to specify how I want to differentiate. So I need a connection to the tangent. In Rn, it's clear how to differentiate. On manifolds, unfortunately not. But if we pick a Riemannian metric, it will define for us the so-called Levi-Civita connection. Riemannian metric probably you heard, that just means that every tangent space of the manifold, I have a scalar product, so we can talk about length of vectors, angles between vectors. And the Levi-Civita connection preserves all this. So if I parallelly translate with respect to the Levi-Civita connection, then angles and length vectors are preserved. So, as I said before, if I am on the Riemannian manifold and I fix a point P, I get the holonomy group of M and G at that point P, and that's a subgroup of the orthogonal group of the tangent space at that point, which is generated by all parallel translations along closed smooth loops. And actually, it's a closed subgroup, maybe that didn't fit on the slides. And closed subgroups of ON, well, I think are pretty well understood. So nothing bad is happening here. And what holonomy does for us is, well, assuming that our manifold is connected, I can connect any 2 points by some kind of curve, and I can do parallel translation from one point to another. And now I can ask which structures can I define at one point in the manifold so that they are parallelly translated everywhere without any contradictions. And that works exactly if the structure at my origin P is invariant under the holonomy. So now connected to one topic of this conference, representation theory. We'll see some structures on the G2 manifold which we can define at one point, which then get translated everywhere using parallel translation. If you are a topologist and you've been working with vector bundles, say, then you probably know the concept of a structure group, which means for a vector bundle, you always have a prime bundle, but if you can pick a sub-bundle of the frame bundle for a smaller group than GLN, then typically you can say more about the vector. And holonomy, I would say, is a geometric version of this concept, where we are allowed only reductions which still contain the holonomy groups. So everything reduced should also still be parallel. Okay. So things that I can define at one point P that would include the scalar product. I said that's invariant under the Levi-Civita connection, so that is everywhere. Or from a more global point of view, if the holonomy group is inside SON, then it preserves an orientation at one point, and therefore have a global orientation in the matrix. So that's the point-wise to global aspect of holonomy. Any questions up to this point? So Berger noticed that not every subgroup of N can occur as a holonomy group. And if we want to give a rather short list, we should exclude all Riemannian symmetric spaces. They have their own holonomy groups. We should also exclude Riemannian products, because then the holonomy group is just the product of the holonomy group of the pieces. And we also say we want to be simply connected so that we don't have effects from the fundamental group kind. And then there's this list of groups, and you will have seen a lot of them probably before, like for example, you might have seen scalar manifolds at some point, or Calabi-Yau manifolds. These are the groups UK and SUK. There are some quaternion analogs of those. And then there are these two exceptional groups, G2 and spin 7, and I would like to focus on G2. And the rest of the table, well, that is the dimension of the manifolds where that happens. That's 7 in our case. The Ricci curvature is 0. In fact, if anybody knows a reason why this list divides into two pieces, one piece contains the Ricci flat manifolds, and the other part is those which have models as Riemannian symmetric spaces, say sphere, complex projective space, or coordinate projective space. Yeah, if anybody can give me a good reason for that, I'm very grateful. I don't know if that's known. Okay, so we are in for G2s. And why G2? There is a mathematical motivation. It's the only special holonomy group that occurs in odd dimensions. So there will be a lot will be different from other holonomy groups. And together with spin 7, these are the only groups which don't have any obvious connection to algebraic geometry. So you're definitely out of your comfort zone. Yeah? So you need some new methods, and that makes it interesting, I believe. From a physical point of view, well, physical in scary quotes, you remember that in string theory, space-time takes the form of a four-dimensional visible space-time in the Calabi-Yau manifold. And in M theory, you take a product with a G2 manifold instead of a Calabi. And M theory is believed, as well as string theory, to satisfy the greatest problem in theoretical physics, which is unifying gravity and quantum field theory, but I can't say anything about that. There are some possible relations to other physical theories that we hope for fruitful interactions. Like, for example, yesterday we have seen in other areas what physics intuition can lead to, and here we hope for similar input. So now, let's get concrete. If you have a 7-dimensional oriented manifold, then you can pick a differential form of E3 called phi, and we say that this form is non-degenerate if at every point P of the manifold and for every pair of linear independent vectors U and V, you find a third vector W such that phi applied to the triple is non-zero. Like a scalar form is non-degenerate, it means for every vector you find a second vector so that the result is non-zero. And here you have to start with a pair. Okay, if that is the case, then there is a unique symmetric bilinear form G phi on your manifold. And if you write the strange formula, you plug in one vector into phi, then you wedge with phi with the second vector in it, and then you wedge with phi just as it is. You count this, that's the 7 form. Then the idea is this should be 6 times G phi of V and W times the volume form that is associated to this. And this is a strange way of defining G phi because the volume form there also depends on G phi, but you can show that there is only one solution to this. And then this is again a bit of representation theory, if you like. You get a bilinear form and you ask for a signature. So that's the largest dimension of the positive eigenspace and the largest dimension of the negative one. And there are only these 4 possibilities: 7, 0, 4, 3, 3, 4, or 0, 7. And if we are in the first case, then we call phi positive. Actually, if we change the orientation, then this 2 entries in the signature change. So you could have done with only 2 of these pairs. But we have fixed an orientation so that we can say which 3 forms are positive. And if G phi now is positive, then we have our remaining metric. And so we say that a positive free-form phi defines a G2 structure. This means the structure group of the tangent bundle is reduced from the general linear group in dimension 7 to G2. This doesn't say anything about holonomy yet, but at least point-wise, we have the right structure. And there's another form I should mention. So if phi is positive and you have the metric, you can take the Hodge star of phi. That's the 4 form, and if you haven't seen it, that's the geometric way of doing Poincare duality. So you have a 4 form now, and this 4 form isn't quite non-degenerate. But if you have a triple of 3 vectors, UV and W, on which phi vanishes, then at least you find a 4th vector x so that psi doesn't vanish. Okay? So it's kind of, psi is kind of, how should I say, non-degenerate with, relative to phi. And this condition will appear once more at the end of this first talk. Okay. So, now coming from a different direction, I don't know how you imagine the group G2 if you do it all, but for me it's the automorphism group of the octonions. And that means the invariant, the imaginary octonions form an invariant 7-dimensional subspace. And that's the model that we are using for our G2 manifolds. And now there is a unique scalar product on the octonions, and that's the octonion multiplication. And you can combine these 3 things to get a 3-form phi 0. That's the model of a positive 3. The stabilizer of this 3-form in the general linear group is exactly G2. So that fits with the previous slide. And the funny thing is that the GL7 orbit of phi 0 in all 3 forms on R7 is open, but it is not dense. And yeah, it's not dense because the orbit for the other signatures is also open, and you have degenerate 3 forms in between. But somehow a phenomenon like this tells you that you are out of the algebraic geometry. Yeah. That typically open baskets. So now finally to get to G2 holonomy. We take a positive 3 form on M, so we have our G2 structure and our metric. And because it's a 3 form, you can take the exterior differential and ask if it's closed. And you can take the differential, the dual of the differential with respect to the L2 metric. And you can ask that that one is closed as well, and that's equivalent to saying that the form psi from the previous slide is also closed. If you have these 2 conditions, then you say that your 3 form is torsion-free. And well, this looks linear on the first glance, but remember that the adjoint of D is taken with respect to the metric G phi, and G phi depends on phi. So in fact, this is a highly nonlinear. It just looks nice, but it's not. So this happens if and only if the 3 form phi is parallel with respect to the Lev-Childa connection. This is something you have to prove. And once you know that the holonomy group must stabilize your positive 3 form, and since phi 0 is a model for that form, you see that your holonomy group must be a subgroup of G2. Okay, we're getting closer. We are now considering manifolds whose holonomy is a subgroup of G2. Next thing you notice is G2 is simply connected. So G2 manifolds are automatically spin, can always live from a standard representation of SO7 to a spin representation. That's the condition. And another way to look at G2 structures, well, the stabilizer of the non-zero element of the spinor bundle is G2, no matter which one you take. And so a Riemannian 7 manifold has holonomy contained in G2 if and only if it is spin and there exists a non-zero parallel spinner. So from physics, lingo somehow spinner means section of the spinner bundle. You're not allowed to say spinner field, but you're allowed. Okay. Now let's see what other structures we might have on a G2 manifold. So the G2 structure induces splittings of the exterior algebra. Nothing interesting happens in degree 0 and 1, but in degree 2, you see there is a 7-dimensional component of the two forms and a 14-dimensional component. In fact, the 14 is the dimension of G2. That one corresponds to the Lie algebra G2. And the 7 is the dimension of the tangent bundle, and you get these, the two forms there you get by inserting a vector field into this form. So that explains the splitting of lambda 2. There is a similar splitting of lambda 3. Again, now there is a one-dimensional component, that's where the form phi itself lives. There is another component isomorphic to the tangent bundle, you get it from the 4 form, and some spurious remainder. And then, because you have the Hutch-Star operator, the same happens in lambda 4, lambda 5, lambda 6, lambda 7. And I already said the subscript is the rank of the bundle, and if the rank is the same, then in this case, in the G2 case, these bundles are isomorphic. Now comes a little theorem by Joyce. You could call it a Hodge-Lefschetz decomposition. It says, first of all, that the rank homology respects the splitting on a G2 holonomy manifold. And second, and that's more interesting, if you have now homology groups with the same, cohomology groups with the same subscript k, for example, you see for k equal to 7, there's quite a lot going on, then the corresponding cohomology groups are isomorphic. And if you are actually in holonomy G2 and not just a subgroup, then these 7-dimensional pieces all vanish. So here you have the first obstruction against G2 holonomy. The first Betti number must be 0. And what you could do, you could look at subcomplexes of the Durand complex by projecting the differential if necessary, or restricting and projecting. There is a red one which only contains forms from degree 0 to degree 3. You can see it up there also. There's the blue one that starts with 2 forms, goes into 3 forms, and then you take the analogous part of the 4 forms and the analogous part of 5 forms, and that's it. And what's left is then the black one over here, which is isomorphic to the red one. Okay, so there are some subcomplexes like you are used to working with, say, anti-holomorphic forms, scalar manifolds. You could do something similar here, except we have that part of what it's good. Except for, no, it's good for defining instantons, but that comes later. So, what are now obstructions against having holonomy G2? First of all, let's assume that we have a subset of G2 as our holonomy group. We've already seen M must be oriented in spin. So these are 2 obstructions. Next one, phi is a parallel 3 form, so it's actually a non-vanishing cohomology class, and therefore the third Betti number should be at least 1. Then, if we have holonomy G2, our manifold is richly flat, and we learn by Chiga-Gromol, for example, that the fundamental group of the manifold must be finite. If it was infinite, I would be able to take a universal cover, and that would split off a line, and my holonomy group would be reduced. Now, on the representation theory we just had, on the exterior algebra, I can hook up a form, a symmetric product on the second cohomology by picking the round representatives, pairing them with phi, and then integrating over n. You see the integral, the integrand has degree 7, so that's defined. And this form has to be negative definite. They go somewhere into this, and this only happens if the holonomy is exactly G2, because otherwise we would have the 7-dimensional representations, which would destroy the picture. And for a very similar reason, if I take the first Pontryagin class of the manifold, it has a representative being a linear combination of squares or freeforms, and therefore also its pairing with phi must be negative. These are maybe the most interesting obstructions, and we'll keep them in mind for the second half of the talk. And these are all obstructions against holonomy G2 known to me. If you have one more, let me know, I will be happy.
For the last two bullets, I assume you could also assume it's a subset of G2.
No, I think not, because then I could have a 7-dimensional piece, and there it doesn't hold. So if alpha would be a clean form of type 7, I don't get this inequality. Now, the moduli space is promised in the title. So you take the set of all positive contortions to free forms. That's typically ugly, infinite dimensional, whatever, Cauchy space, don't care. Then you take the connected component of the diffeomorphism group, call it the M, and you say the G2 moduli space M is the space of these positive and torsion G2 structures divided by the diffeomorphism group, which acts by pullback, and we call this the G2 moduli space of A. And, well, I mean, you are typically used to getting now a very explicit description of your modular space. Like in algebraic geometry, you would expect me to write down a set of equations and say this is it. Or you expect me to write down some category and say the nerve of it is our modular space. Unfortunately, all these methods don't work yet in this context. We have no nice conceptual description of the modular space. The only thing we know is this theorem by Joyce. Well, I think Torelli theorem is a bit, it's maybe a bit too great a name for the result. It says that the G2 modular space is a manifold, and the map which sends the class of a positive and torsion-free free form in the modular space to its class in the third cohomology. This is a local difference. And I mean, I have written this on purpose, like it looks like the identity, but of course it's not, because the equivalence relations on both sides are totally different. But still, this is how to memorize the theorem. There is a local diffeomorphism from the modular space into the tree, into the third cohomology. And we don't know really much about the global structure of this modular space. So first of all, this map, we neither know if it's injective nor if it's surgical. Yeah. The only thing we know about the modular space is that it's not connected, and I'll tell you this in a few slides. And we know it's not aspherical, and I don't want to spoil it too much, but you should go to Thorsten's talk in the afternoon. He will tell you why that's the case. So if we want to understand the modular space, currently our only chance is to construct all of its points, which means to construct all examples of G2 manifolds. Maybe of a given diffeomorphism type, whatever. But that's, at the moment, the only technology we have. Feels a bit like Stone Age, but that's it. The first non-complete examples were constructed by Bryant. In fact, there are cones over nearly scalar manifold, with a rather algebraic construction. Then Bryant and Salomon found complete manifolds, which are asymptotic to these cones. Then a while later, Joyce came up with his first closed examples. Maybe you know the Kummer construction of a K3 surface. You take a 4 torus, divide out by an evolution, then you get 16 singularities. You blow these singularities up, or you smooth them out, or do something similar. And whatever you do in the end, you get a K3 surface. And Joyce did pretty much the same, but starting from a 7 torus, and I guess Thorsten is also explaining a bit more of that. And there is a generalization of this by Joyce and Karigiannis, which say that you could actually start with a G2 manifold, divide out by an evolution, so you get a G2 orbifold, and then you can try to resolve it. And there is one more construction that goes back to Donaldson, but was first worked out by Cavalier, and then later in more detail and with many more examples by Claudia Haskins, not to Pacini. That's called twisted connected sums. There you start with 2 building blocks formed from asymptotically cylindrical Cavalier manifolds, and you stick them together in a strange way, whatever. Yeah. I like to talk about these things today. And we have it together with Sterling Crowley and Johannes Nordström, we have added a little extra twist to this. And maybe you will see a few slides later what this extra twist is good for. So, what are now the important open problems in G2 geometry? First of all, you can see all these constructions above somehow come by regularizing something singular, or if you stick two pieces together, you can imagine you tear them away far from each other. And in each case, you always get very quickly to the boundary of the moduli space. So it looks like you have the moduli space, but the only thing you can actually attack is very close to the boundary. You can come from the outside, walk in a bit, and that's it. Yeah, and the rest is here behind.
You mean by boundary? You said it was smooth. Let's talk about any boundary.
I'm imagining there is a boundary. I know it's not really defined.
Is that infinity or what?
Yeah, it's like sometimes it's infinity with the twisted connected sums. With the Joyce examples, it's like probably in the middle. Or not orbital points, strange points, little singular points. So you could imagine you take one of these examples and try to push far away from the boundary as far as you can before they become singular again. And then you would have at least like gone to the bar and then cross the island until you get to the other side. You still don't know the whole island of sky, but at least you have found one pass through it. And even that seems to be difficult for G2 manifolds. So the question is, how far can you deform a given metric? We don't know. And now, for the physicists among us, you may want to construct G2 metrics on singular spaces with very particular and very, very difficult singularities, because I've been told by physicists that only then you would see in your M theory a gauge theory with a non-Euclidean gauge group and with massless chiral fermions. So G2 manifolds, as nice as they are totally worthless, it seems. Well, you need singular stuff, which is even more difficult. Any questions? Okay. So now topology, that's what we are doing, right? So the basic topological invariance of a 7 manifold with holonomy G2, well, we have the fundamental group, and I've told you it's finite. Then, of course, we have the second and the third homology group, and with that, we know basically most of the cohomology except for maybe cup product. Okay, I just added caveat that. And then M is spin, and that means there is a natural way to take one half of the first boundary eigenclass. That's a class in H4 of M. And I believe these are basically the most important invariants which don't use the G2 structure too much. And now Dermot Crowley and Johannes Nordström found a few more invariants. And for this, we assume for simplicity that M is simply connected, well, oriented in spin, we know, and we assume that H4 of M is torsion. And now we take the divisibility of the half Pontryagin class by Ruth's formulas, that's an even number for the D, and we take the least common multiple of D and 4 and call this D twiddle. And now, if you have a G2 structure on M, you can define 3 more invariants. The first one doesn't even depend on the D2 structure, that's a version of the Ilstorfer invariant with values in Z mod the greatest common divisor of 28 and D twiddle over 4. Then the new invariant is something which I'll say a little bit on the next slides that lives in Z mod 48. And then there's another invariant called psi, which lives in Z mod 3 times D twiddle. And these invariants satisfy some relations. For example, the psi invariant is always congruent to 7 times the new invariant of 12. And because of this, you can take the difference, divide by 12, and that will then be congruent to the Ilstorfer modulo this denominator of D. So this is a little bit more that you can learn if you consider the G2 structure space, not the modular space for holonomy, but the space of G2 structures from a topological point of view, and you get these extra invariants here. And let me just give you a very vague idea of the new invariant. So I told you that G2 holonomy means you have a parallel spinner. And if you want just a G2 structure, you could say, let's have a non-vanishing spinner, maybe of unit length, whatever. If that's the case, then you can take, you can think that the spinner bundle has dimension 8. And if you take a local trivialization, it's just some hash of R7 times R8. And the unit sphere in the fibers, that's S7. So it's basically maps from a patch to S7, which you can believe to be constant, but then you take connected sums with the 7th sphere, and you see that the fundamental, the 7th homotopy group of S7, which is integers, acts by connected sum on the set of G2 structures. And this action is in fact transitive, and it's free. So you have a Z torsor, if you like. And now you find out that you can pull back your structures by self-diffeomorphisms of M, and you will always get multiples of 24. Actually, the divisibility of the first Pontryagin class can lead to the fact that sometimes it's 24, sometimes 48, maybe sometimes 72 or something like that. With 24, you're always in 6. So you should mod out 24 in some way. And indeed, Crowley and Nordström found that there is an invariant mu from this G2 structure space, modulo homotopy and diffeos to Z mod 48. But it doesn't take all 48 values, it only takes those which have the same parity as the Cabert semiconductors. So it's always the 24 values that you would expect from the line bubble. And in the side, a student of mine once proved that if you take the new invariant mod 3, it detects the stable, the unstable tangential cobordism classes. I mean, spin's cobordism is trivial in dimension 7, but if you want a G2 structure, there are exactly 3 cobordism classes, and they are found by nu. So we have an invariant. We can ask if it's non-trivial. If it's trivial, we can throw it away, or we can say, okay, we have found a property of something. So assume we have G2 holonomy. We are in a subset of this G2 structure space, right? So on the subset, maybe the invariant becomes trivial, then we would get an abstraction against G2 structures. Or maybe Riemann 3 is trivial, then the G2 cobordism class will present an obstruction. Or maybe we are lucky and we can realize many, many different values of mu, and then we have a new method to distinguish them. So topology is helping G2 geometry either way, no matter what the answer is. But then, well, you have to find a way to compute the new invariant. Its original definition involves cobordism, so you have a G2 manifold, then you have to find a cobordism, a spin cobordism. The spin cobordism group is trivial, so you always find it, but can you do it explicitly? Well, so we looked for intrinsic description and we found an invariant mu bar with values in Z mod 48 for G2 structures, but in the case of G2 holonomy, it's actually integer. I mean, I don't know if you've read the papers by Craig and Stoltz about the Ilscoifer invariant. They show that the Ilscoifer invariant has lived to the integer if you have positive scalar curvature, and this result is pretty similar to that. And for normalization reasons, I have to add 24 times 1 plus a first value number. So the next thing we did is we were looking for 7 manifolds with different G2 metrics on them, which have different mu bar invariants. Sometimes they differ exactly by 40. So how do you do this? You have these constructions of G2 manifolds, and you take two constructions with different parameters, say, and then you compute so many differential topological invariants that you get from some classification results by Wall and Wilkins and Crowley that, in fact, they must be diffeomorphic. But you don't know the diffeomorphism, you just know they're abstractly diffeomorphic, and then you also compute the new invariants and find out that they are different. So this is a very abstract result. Can't really draw you a picture of the 7 manifold and draw you a picture of one G2 metric and one of the other. That's not, unfortunately, not possible. But notice that sometimes the difference is exactly 40 and sometimes it's something else. Also, together with Johannes, we found out that all odd elements of Z mod 48 are attained by G2 manifolds. And we conjecture that this also holds for the even values, but we were too lazy to figure that out because it would be a slightly different construction with a bit of more work. Yeah. Now, let's see what we can deduce now. First of all, the moduli space is not connected for certain n, simply because there are different values of the new invariant. I think that's not clear. And more interesting, I guess, if you have one connected component of the G2 structure space, and you find two G2 metrics whose new invariants differ by 48, well, they are still in the same component of the structure space, but if you want to lift it up to holonomy, you see that the connected components are different and very well separated. Then, bad result, if you like, is neither G2 cobordism nor mu seem to give new obstructions against holonomy G2. And I also mentioned the Xi invariant, and the student of Johannes has found some more components of the G2 modular space which are distinguished by Xi, however, the new invariants are the same values. So this is, I think this is a good example where you see that from topological considerations, you can actually give some input into G2. And I believe that's the reason why I'm standing here and trying to convince you that this is interesting. Yeah, questions up to here? Well, let's summarize once more. There are only few obstructions against G2 holonomy. There are only few compact examples. Well, few, I mean, it's 10 to the 8 information families, but most of them are of one type. So they still have different diffeomorphism types, but the construction is always the same. There should be much more. Known compact examples, as I said, are always close to the boundary of the moduli space, possibly the boundary of infinity. So it's in the end of the moduli space, if you like. And some important open problems, you want to get more invariance for G2 manifolds or more obstructions against them so that you get closer to the range of examples. Of course, you also want more constructions. Then something we don't know is the relation of the equivalence class of phi in the moduli space and in the third cohomology. I mean, from a conceptual point of view, we don't really understand what's going on. And as I said, we neither know the map there between these two spaces is injective nor surgical. That's it already, okay. Any questions about this topological part? Yeah.
That might be very handy, but is there a nice reduction of moduli space?
I believe sometimes you could have other components of the diffeomorphism group which would then act. And if you let them act, maybe you get orbital points. But this depends on the manifold you are on, I believe. So nothing nice conceptual, I believe. Not that I know. No, I mean, you have to ask many questions if you can't ask informed questions. And I guess in vitro geometry, it's hard to ask informed questions. So I think any question you ask is very fun. Might lead to some ideas. Okay, so last part of this talk, some analytic aspects about submanifolds, and don't be afraid. The worst you'll ever see is easy inequalities like here. So if you have a K-form on a Riemannian manifold, you call it a calibration if it's closed, and whenever you plug in vectors into the form so that you get a number, then this number is smaller than the k-dimensional volume element of the metric applied to those vectors. D-vol looks like a positive differential form, but in this case, it's just a volume. And we say that an oriented submanifold is calibrated by such a form alpha if the restriction of alpha to the submanifold is the volume form of the restricted Riemannian metric. Now, why is this interesting? Because assume you have a second manifold B, and you have a little cobordism W between A and B inside M. And then if A is calibrated, you can use Stokes' theorem, and you can start with the volume of B. And because of the inequality up there, the volume of B is larger or equal than the integer of alpha, because pointwise alpha is smaller or equal than the volume element. And then by Stokes, this is the same as integrating alpha minus the integral of d alpha over W, but d alpha is 0. So you have the integral of alpha over A, but alpha is the volume element. So you see that the volume of B is always larger or equal than the volume of A. Hence, A is a minimal submanifold. And actually, if you ever try to prove that the shortest curve between 2 points in the Euclidean space is a line, then you probably have to apply an argument like this. So this shouldn't be entirely unconvenient. Yeah, so this is what a calibrated submanifold is. For example, you are in a Kähler setting, then holomorphic curves are calibrated to submanifolds. They are calibrated by the Kähler. Other complex submanifolds are calibrated by some powers of the Kähler form, possibly divided by some constant t, so that the condition number 2 of their holds. So that's a typical application of calibrations, if you like. And if you are in a Calabi-Yau manifold, you also have a holomorphic volume form. And then say you pick its real part, And that calibrates what's called a special Lagrange. Or you multiply with some phase function first, so you see different special Lagranges. So this is calibrated, these are calibrated submanifolds. They play a role, in particular in complex geometry. So one can ask by analogy, do they play a role in G2 geometry? Let's start with the easier case. So we take the Hodge star of the three form phi that was called psi, it's a 4 form, and phi and psi are both calibrations. And we consider submanifolds calibrated by psi, and they are called coassociative. For whatever reason, it's kind of complementary to associative, and I'll give the reason for associative on the next slide. But coassociatives are easier. One other condition is a submanifold is coassociative if and only if the three form restricts to 0 entirely. So if we have such a positive form which is closed, and we have a closed-oriented form manifold, we define the moduli space of coassociative embeddings, M coas of M5X. That's the space of emergence from X to M, embeddings, let's say, such that the pullback of the three form is 0. And we mod out by the unit component of the diffeomorphism X. So here we have another moduli space, which is somehow associated to the G2 structure, which explains the word there in my title. So there's more than one modular space, and now you could ask what you can learn from the associative submanifolds about the G2 manifold. First of all, if you have given one, you want to know if there are others nearby. And there's a theorem by McLean which tells you basically that this coassociative modular space is always a V2 plus of X dimensional manifold. So you have an oriented form manifold, you know the second homology splits into self-dual and self-dual. You take the self-dual Bethe number. I mean, it depends on conventions. Other people take the negative one, but I'll tell you why it's a positive one in a moment. Assume X was a K3 surface. Then you know that B2 plus is exactly 3. Also, you know that it's the hyperkähler complex structures on the K3 surface which give you this B2 plus, and they vanish nowhere. And now, if you know how this McLean theorem works, you deduce from this that you can take a K3 surface and move it a little bit in every possible normal direction. So a little tubular neighborhood of the K3 surface is going to be foliated by K3 surfaces again. And sometimes you are lucky and you can extend this to a singular foliation of the whole tube. And then you have a lot of structure, and then you can start thinking about that. There is a paper by Donaldson where he considers that situation in a limit where these K3 surfaces get very, very small. You even can describe the asymptotic geometry of that. So you see that this coassociative theory, if you like, might give a clue to understand the geometry of certain G2 manifolds much better. Now to the associative submanifolds. Those are calibrated by phi, so again they are minimal. And they are called associative because you could take the psi, the form psi, and turn it into a three form with values in the tangent bundle by applying the Riemannian metric. And if you do this, you get this capital psi, and in our model situation on the imaginary octonions, capital psi is exactly the associative up to a factor of 2. So it tells you if you are on an associative subspace of the imaginary octonions, that it vanishes. And that's exactly the case if you're calibrated by phi. So the submanifold is associative if and only if the associator vanishes on it, and that maybe justifies the name. And now coassociative subspaces are exactly orthogonal to the associative ones, and that justifies the other. And now it gets a bit complicated. A generic, in scary quotes, closed associative submanifold is rigid, which means you cannot deform it. There's only one that's isolated. And the only thing you can hope for is if you move the G2 structure a bit, that this associative submanifold deforms with the G2 structure. Now, generic looks like it was a nice word, but in fact here it only means that the kernel of a differential operator that has a chance of being invertible is actually zero. But you are in a very specific geometric setting, so maybe it's not generic at all when this happens. Okay, let's consider the combined G2 and associative moduli space. So we pick all G2 structures phi and all embeddings of the three manifold into M, such that M and phi is the manifold of holonomy G2, and the image of iota of this embedding is an associative submanifold that has a natural action by both the diffeomorphism groups of M and X. You divide both of them out. And if you consider now the map from this combined associative and G2 moduli space to the D2 moduli space, just by forgetting the associative, then at these so-called generic points, this map is a local difference. But as I said, it's not at all clear if generic is really generic. But anyway, if you imagine you have a covering of the G2 moduli space, then you can start thinking about, well, maybe it has a deck transformation group, or maybe you can count at least the fibers. Well, there are many homology classes, and the homology class of an associative, it's one of its invariants. So maybe you want to count only in one homology class. And then you wonder, if you can count, you wonder how does the count change when phi varies. But as I said, all this hinges on the notion of generic, which is maybe not as generic as it should be. Good. One more thing in the end, instantons, that's a slightly different subject. You pick a vector bundle on your manifold, comes with a principal G bundle, say, and you consider a G connection on that principal bundle, and you call this an instanton if its curvature satisfies this harmless looking equation that the curvature which psi equals 0. This is a differential equation because the curvature arises by applying some differential operator to the connection itself. It's basically squaring the connection. So this is a nonlinear differential equation there, even if it looks harmless. And the consequence of being G2 instanton is that you minimize the Young-Mills energy of that connection. Whatever the Young-Mills energy is, if you don't know, don't worry. The only thing we care about right now is that from the deformation behavior, instantons behave quite similar to associative submanifolds. Also, by Donaldson, Siegel, Heidelberg-Ruski, whatever, a generic instanton is, sorry, that comes later. A generic instanton is rigid, so it cannot be deformed. But maybe if you deform phi, it will vary, so you will have a combined instanton and G2 moduli space as before, and you can ask very similar counting questions. But instantons can degenerate along associative submanifolds, so basically the bundle will be flat. Outside the submanifold, we will have an infinite curvature concentrated along the submanifold. And therefore, conjecturally, if you count, you should maybe count instantons together with associative submanifolds. And that's then called the Donaldson-Siegel program. That's a very nice program that we are very far from understanding. Maybe I don't have much time. Here's a way to relax the problem a bit so that it's a bit less cumbersome. So you want to close three form, you want to close four form. We don't demand that the four form is the hot star of the three form as before. So they are basically coupled now. but still you want the product to be positive, and you still want that somehow psi is non-degenerate relative to phi in the same sense as like half an hour ago. And if you do that, you can still define associative and coassociative submanifolds. You can still define instantons. And you hope that in this context, the term generic is actually more generic than it was before. But you should also know these objects are no longer minimal, but the deformation theory works exactly as before. And if you really want to pursue the Donaldson-Siegel program, then it's maybe better in this context where everything is a bit nicer. Okay, but we'll not come back to this in the second half. It's just to tell you that all the analysts have thought about making things easier. So to summarize, co-associative submanifolds have nice moduli spaces, and sometimes they even foliate N. Actually, we also know examples of coassociative submanifolds that exist in nature, at least in some of those examples. And I think the foliations are some of the twisted connected sums. So generic associative submanifolds are isolated and they deform with phi, and maybe it's a good idea to count them. And generic G2 instantons behave similar, and maybe if you count them, that corrects the count of the associatives. And everything becomes a bit nicer in the case of almost 10 G2 structures, but apart from that, we don't know much. And so we'll look for an entirely different approach in the second half of the talk. And that's it for now.
Thanks, Sebastian. Questions for the speaker?
Yeah.
These things where the associative submanifolds foliate your manifold. Is it possible that, like, away from the singular leads, you actually get like a fiber of your manifold?
Oh, yeah. So fiber bundle also have the singularities. And if the fibers are very small, then you can give a nice geometric interpretation. So the base will be an F3, if I understand correctly, with and the singular set will form a graph of F3, and you now map it at the maximal surface into the K3 modular space. The K3 modular space has a remaining metric of signatures 3, and G. And then it makes sense to talk about maximal submanifolds like, light curves are maximum curves in Lorentzian geometry. That's, oh, sorry. Yeah. No. Unaccelerated time-like arcs. Sorry, matrix. But anyway, it makes sense, and there's a very complete geometrical picture, but only the K3 surface is small and the rest is really large. Okay. Yeah.
Means the theory that associative manifolds are rigid, was the box size also, because if you drop this condition, can you find, and then you only know that your form phi is closed, and can you say something about generic? Like a generic statement for this form, for example,
so I personally definitely can't say anything about that. McLean wants the 4 form to be closed, that's true. The 3 form, he doesn't care about the 3 form, so he doesn't care about the thing being calibrated, it's only the other condition. But I don't know, I mean, if it's still closed, you could still ask if there is something calibrated. Maybe that's hopefully overdetermined now. Hope less than overdetermined, so.
If there are no further questions, let's thank the speaker again. Menü aus, macht ihr das explizit oder ist das wieder das mit einer Klassifikation? Ist das wieder so die Motion?
Von der Gefahr ging es
basically,
ja, wenn wir was machen, warum Yes. Oh, really? Who? Yeah. Do exactly what you were saying. I would do more. So that's why I was so yeah. Yeah. And she left her body that motion is very good. It's the connection. Yeah, yeah. Yeah, because us, yeah, that's okay. Yeah. Well, yeah, cross training is good. I mean, parents are probably very good at cross training. They come up with a But we will try to get certain half of the system is 2005. So it's not going to be you're seeing people play next, but taking I don't need to do it, but it's not, yes, exactly, seems to be, like, it's It's getting pretty stale. Okay, so you have the bolt. Yeah, and then you'll have to write this stuff. Because Victor told me you knew how to do this like 6 months ago.
Yeah. One thing that Victor didn't communicate to me was that anybody cared. They didn't do tensor categories like in the beginning of the so I had no idea what some. Okay, and
Well, you know, I think it's the kind of thing where like it's, I think people care because it would just be convenient and it's like nice, I'm not sure anyone like actually needs it right now.
Yeah.
But it is very convenient and nice.
Yeah, it's definitely something. But if I knew that like anybody's ever gonna ask me about it, I probably would have put more effort into writing it down in a more reasonable way. So okay, then, so let's start with CA when that's okay, and A is another object, and then so the kind of formalism part of it is that ideals in A, by which I mean some all objects,
Right.
correspond to, and this is a bit wonky, but it actually helps. To see cross stable
Oh,
ideals in in cross there. Okay, so
yeah, you need to explain it.
yeah, so cross A, cross A. Well, it's the category of projected object in model. So in the category of right module objects, right module. So in other words, we can show that this is just the additive closure of objects of the form.
Yeah, every A module is C.
Yeah. So about free or the projected, right? So like you have two different motions, projective and free.
Oh, right.
So because in other yeah, because the form from B tensor A over A blank is like form from B. So if I wanted to project it, then the B has to be projected. So that's what A. When I say ideal here, I mean like the notion of an ideal layer. So like for every home space, I have a substance.
Yeah, you mean not necessarily big ideas.
Yeah, they can be the problem. Actually, interesting ones are the problem. And by simple statement, I mean, okay, so what is an ideal? So we made an ideal J. It's a collection of morphisms, so that F is in J. And I have any G and any.
Oh, the crude.
Yeah, exactly. So
I wouldn't be necessarily stable in this.
yeah.
I don't know what the
Module.
yeah, something, yeah.
Okay.
Yeah, you want stable, I was like, oh, you're doing like some stable patterns.
For us. Yeah, it's more active.
Well, it's a cool result.
The result is, but anyway, so okay. So
You beat I think all the prospect at previous. That's not.
in a way, but
What's a non-direct?
yes, but also, but depends on how much time they put in there. I mean, they did write it down. Well,
I mean, probably people to, I mean, I don't know, I think this, I'm not sure, they probably not spend as much time as you did,
yeah,
but again, a problem that Pavel can solve himself in 5 minutes is usually,
it is highly unclear. Yeah,
well, he's not good.
yeah,
I understand.
fine tuning anyway. So okay, so there is a bijection with this, and I think it's good to like first just take it to granted, and
Sure.
if you can define it for a moment, then I can kind of get to the actual
Yeah, I don't want to give you all the detail, because it's not like something.
yeah. So maybe the bijection follow from this whole like Samba module formalism.
Oh, I see.
So then once you have that, okay.
Could you really, it's like, like,
So then I want to introduce given an object an ideal of the form, which kind of measures the exactness of the module category of the module category. So then okay, we do so when is model and so let's just think for a moment what it is just a chaos, right? Yeah, what's the deal?
see.
Right.
You should definitely not put this on. We should definitely not assume characteristic.
No, but this I don't know. Yes, because I need to function.
Parallel convenience, no, you're fine. Parallel convenience is the news of the doctor. It has nothing to do. Like previous parallel dimension always lends in C, no matter what you consider. Anyway, it's different. You're fine. Don't worry about this. Okay. So A is a and parallel convenience is something that has to do entirely about the prototype gradient. The prototype gradient has nothing to do with the
Yeah.
It maybe has to do with the fact that the field is all the way to close, but like, okay, I'm going to build a lot of it.
Yes, okay, so the field is just an algebraic property, yes, of course. That's right. Okay, so if you have a chaos, and you also have a semi-symbol, and you want to do this in terms of ideals, then you say, well, it's different only in the right.
Yeah.
Okay. It's easy. So I want to introduce a radical. So what I do is I say, okay, so let's in this proper setup, so maybe just to not kind of confuse it for B. So in the proper setup with the algebra object A and C, you let the radical, which is like a C stable radical. Okay. This is okay, so this is supposed to be an ideal of the form. So I need some, and they're supposed to go live on project. Because I'm supposed to define an idea of the start space and the whole space. And well, I consider a lot of this F goes from F is supposed to be the radical idea itself, and non-radical, this is why I have substitute C to distinguish the C stable radical and just the ordinary homotopological radical. So this is supposed to be a radical such that if I hit it with a projector, this is also radical. So I hit it with a projector, and it becomes around. And it's for all
What do you mean by the radical of the multi-factor? What's radical in?
Yeah, so you can always give an idea. It's determined by the impulse because it extends into the direct sum and direct sum. And so if I'm an n impulse, this is home, and then if n is not n, and it's the radical of the endomorphism algebra of n if n is the image of the radical of and by radical here I mean you take it one.
Yeah.
So you can characterize this idea as the maximum of the idea in a finite division. So in particular, this idea of the distribution measured the excitement of the multi-distribution is important. So kind of important to consider because I mean this is contained in the ordinary radical. Okay. So you consider this, and then what's the point? Point is that if you have some let's see, now you have some value being array will be in approach. And I want to write what I want to do at the end of the day is to show that P stands for W or P acting as I think it's projected representation. I should try.
I think you're playing those in dimensions.
It might be.
So I take it, projected presentation, and I take it in the middle. Sure. So this is what we have projected curve, and this is the projected curve. So then this morphism Q1 is right. That's the point. This is some homological. So like we have a minimum projected presentation. We can only use the small which determines the projected presentation is a radical. So the Q.
What here radical means what?
Here radical means just the same as what we did before. Like Q1 and Q0 are some projected objects.
So it means nothing unless Q0 is equal to Q1?
No, if Q1 and Q0 are not necessarily decomposed.
Oh, I see.
So you have to extend by matrix to that itself. So Q1 is in the radical of Goette. If we only here we can only this minimum. And now what we do is to show that the projected power is actually in the same. And now using some clever convenience stuff, if I have to buy some projected P prime, so P prime, so P1 is radical. So then it means that Q1 lives in the stable, so it lives in this radical development. And so, okay, now what is the actual? Well, if A is to be simple, it cannot have a proper ideal. But I don't find something in a proper, well, even in a potent ideal, and the potent ideal is either proper or zero. So this means, but this guy has to be zero. But when it's ideal, well, if I have only this infinite modulus, and this is good. Yeah. So the both sides of the conjecture actually we put them in one go because we just introduce something as a measure.
Why can't we probably use for another issue? No, if it's too technical.
Yeah, it is. It's like you need to have the finite projectors, so you can take out some of any inputs and use some the every normal that all the relation of the matrix side of the object. And yeah, this is not something I did. This is something that I just knew the way that is need to check on that. And then yes, then what you obtain is an eigenfunction in the domain, well, in the complexity.
Oh, what, like regular element, or like you did divide, like almost regular element, like just divide some dimensions.
Or is it regular? I mean, you need to go to the complexity. It's not going to be an eigenfunction object. It's going to be like a virtual object.
Yeah, right. So it's like it has to be formula like 1 over like x.
Oh, I have absolutely no idea what the formula would be. You just kind of explain. You show that there is a proper eigenfunction, and then
Is it like like some like every group of different actions and something kind of global?
in
In the complex project.
yes, it's canonical that it follows from the Ferrocardinius theorem, like for the Ferrocardinius ideal.
Like the projection, if the projection onto the eigenspace done by the eigen, which because it's multiple bigger integrants, it's one dimensional. Thank you.
No, I can't really see the missing bits because that's. Yeah, but when I was thinking about this, I got as far as understanding that there was some radical stuff that you could say. Yeah.
Das war ja zu.
Hast du dir den Doktor getragen? Ja. Ich habe auch nicht durch, das war einfach kein Spoiler. Das ist soll ich jetzt zum Schluss das meiner Spieler jetzt nicht was gekauft. Ja, gut, aber wir wissen, wenn die aus dem Haarprinzip gibt es dann Manifolds. Das kann ich nicht sagen. Aber was denn nicht? Das ist kleines für